Hello. Okay. Hi everyone. We will start in some time. I'll wait for people to join for 10 12 minutes and then we'll start. Okay? Okay, I think we should start now. I'll share my screen. Okay, so I hope you have already seen the video lectures for week 4. I will here try to do some questions based on the topics covered in week 4. So some of the topics that were covered in week 4 were continuity, and then a type of discontinuity called the removable discontinuity, and then again like the algebra of limits, algebra of continuous functions, and then some properties like the intermediate value theorem, right, and the sign preserving theorem, and all these things, right? So here we shall discuss the questions. We shall discuss the questions on these topics so that they will help you solve the assignments for week 4, right? Okay. So question number 1. I'm sorry, I'm feeling a little under the weather today. So, all right. Question number 1. The largest subset of R on which the function fx equals cos x square minus pi square upon x square minus pi square is continuous is A. The options are A minus infinity to infinity, B minus infinity to infinity minus the interval minus pi to pi, and C minus infinity to infinity minus the open interval minus pi to pi, and D minus infinity to infinity minus the 2 points minus pi and pi. Okay, so uh, you have to find here the largest set for which this function is continuous. So this is a rational type of function, P upon Q. Just give me a minute. I'm sorry. So we will resume. Yeah. So you have to find the largest set where your function is continuous, right? So you see, this is a rational type of a function, p upon q type, and it is the numerator is a trigonometric function which is always continuous, and denominator is a polynomial function which is always continuous. So as a rational function, it is not continuous if and only if the denominator is 0, right? So we'll say both. Let me use a different color pen. Both x square and cos x square minus pi square and x square minus pi square are continuous everywhere, meaning for all x belonging to R, they are continuous, right? So the function, so fx defined by the ratio x square minus pi square upon x square minus pi square is continuous wherever it is defined. It is defined, and it is defined when x square minus is not equal to 0, that is x is not equal to plus minus pi, that is f is I'm really sorry again. Yeah. So f is continuous on minus infinity to infinity minus pi to pi. Only these 2 points we are not including. So the correct option is D, right? Now question number 2. The largest subset of R, no, not R. The largest subset of 0 to infinity on which the function gx equals sine x square minus pi square upon x square minus pi square is continuous is, your first option is again minus infinity to infinity minus pi to pi. B is pi to infinity. C is 0 to infinity minus pi. And D option is minus infinity to infinity minus pi to pi, right? So again, as the previous question, it is again continuous everywhere except where the denominator is not is 0. So gx is continuous wherever it is defined. That is on minus infinity to infinity minus these 2 points excluding minus pi to pi. But the question says you have to find the largest subset of 0 to infinity where it is continuous, right? So it is continuous on minus infinity to infinity implies it is continuous on 0 to infinity, but 0 to infinity will include pi. So we'll just have to remove. So the largest subset where f is continuous is 0 to infinity minus pi, right? So our correct option will be C. Okay. Next. Next questions are on the intermediate value theorem, that if a continuous function on an closed interval attains uh, continuous function on a closed interval attains every value, any value, if it attains, then, or basically if a continuous function attains the value a and say b, where a is less than b, then the continuous function will attain any value between that, that is any c which is between a and b, then there will exist some d such that ft equals c. So it is very helpful in finding the roots of some equation you have been given, or how, because if you know 2 points where, say, a point of point A where function takes the value a1 and a point B where the function takes the value b1. Suppose a is greater than 0 and a1 is greater than 0 and b1 is less than 0, then you know that between between less than 0 and a greater than 0 value there exists the point 0. So the function has to attain the value 0 if the function is continuous, right? So you say that when it attains the value 0, it simply means that there exists some 0 of the equation, that is there exists some point, say d, between a and b such that fd is 0, meaning d is the root of that equation. So that's how it is very helpful in finding the roots of the equation and determining if the roots, at least if not exact roots, we say that there exists, at least we can say with certainty that there will exist a root between these two values, right? So, and when we are certain about that, Then we use some, if you know that we use some various numerical analysis techniques to move as close to the root as we can. And this is a separate topic altogether called numerical analysis, which is a very interesting subject in itself. So yeah, this is one of the very major application of the intermediate value theorem. All right. Having said that, let's do some questions. So question is, consider finding the roots of the equations x cube minus 4x plus 13 equals to 0 and x cube minus 13x plus 15 equals to 0. You have to see which of the following is true. A. Both the equations have roots in minus 3 to 2. The first equation has root in minus 3 to 2, but the second does not. The second equation has root in minus 3 to 2, but the first equation does not. And of course, the fourth, neither equation has a root in minus 3 to 2. Okay. Now see, you have to determine if both of these equations have root in minus 3 to 2 interval. So our first case is we check at the end points if the function is taking one negative, one positive value, we are certain that the equation will have a root, because the given functions are of course continuous. They are a polynomial type function, right? Not polynomial type function, they are exactly polynomials of degree 3. So if the endpoints have the same sign, the function value at the endpoints have the same sign, then we cannot say that the equation does not have a root. We can go more inside of the interval, right? And if we can find 2 points inside the interval which have different signs, which give the different signs, then also we can determine the root. But our first guess is of course to start with the endpoints. So let's see. Firstly, consider fx equals x cube minus 4x plus 13. So f of minus 3 is minus 3 cube minus, it comes out to be minus 27 minus 27 plus yeah, it's correct, right? 13 25 27 minus 2. So this is less than 0. Now minus 3 to 2, f of 2 is 2 cube minus 4 into 2 plus 13. 2 cube is 8 minus 8 plus 13, which is 13, which is positive. So since 0 belongs to minus 2 comma 13 implies by intermediate value theorem, as f is continuous on minus 3 to 2, we can say implies f will attain the value 0. That is, there exists some d belonging to minus 3 to 2 such that f of d is 0, implies d cube minus 4d plus 13 is 0, implies d is the root of fx and d lies between minus 3 to 2, of course. So um, so option D is incorrect. At least fx has a root, right? So second equation has root, but for again C is incorrect, so we have to choose between A and B. So now we'll move to the second equation, gx. What was gx? X cube minus 3x plus 15. Again, we'll check it the endpoints first. G of minus 3 is minus 27 plus 9 plus 15. This is 10, 15 plus 9, 24 minus 27 minus 3 less than 0. G of 2 is 8 minus 6 plus 15, 15 plus 2, which is positive. Right? Implies as above, G also has a root between minus 3 to 2. So our correct option is A, that both the equations have root between minus 3 to 2, right? Alright. Next question. Again, it is on finding the roots. Consider finding the roots of the equations x cube minus x minus 5 equals to 0 and x cube minus 2x plus 3 equals to 0 in the interval minus 2 comma 2. Okay. Which of the following is false? False, you have to see. Okay. One of the equations has a root in 1 to 2. One of the equations has a root in minus 2 to minus 1. C, in minus 2 to 2, one equation has a root alpha and other has a root beta, so that alpha minus beta is greater than equal to 2. D, the difference between any root of one equation and any root of other equation is at most 2. So, but in the interval minus 2 to 2, you have been asked to determine the roots of two equations. Then one option is between 1 to 2 interval and the other is minus 2 to minus 1. Then the third and fourth options are upon the difference of the roots. Let's see now. So consider fx first. Fx is x cube minus x minus 5. So f1 is 1 minus 1 minus 5 minus 5 less than 0. F of 2 is 8 minus 1 minus 5, 2 greater than 0. So implies again f is continuous, f has a root in minus 1 to 1 to 2, right? So we have to choose which is the false option. So one of the equation has a root in 1 to 2. This is correct, right? Then g of x is x cube minus 2x plus 3. So g of minus 2 is minus 8 plus 4 plus 3 minus 1 less than 0. G of what was the point? Minus 1. Minus 1 is minus 1 plus 2 plus 3, which is positive. So again, G has a root in minus 2 to minus 1, right? Now say if this root is say A, say B, right? So we have to see now A is greater than 1 always because A belongs to, this was B, okay, as A belongs to 1 to 2, and B is greater than -2 as B belongs to -2 to -1. So implies minus B is less than 2. So B is, we'll see B is less than -1. Implies as B belongs to this. So minus B, I'm multiplying with the negative, minus B is greater than 1. So A minus B is greater than 1 minus B is greater than 1 plus 1, 2, right? So A minus B is greater than 2. So the C option was in -1 to 2, if one root is alpha, if any one root is alpha, there can be one more than one root. If one equation has a root alpha and other equation has a root beta, if one equation has a root say alpha where I supposed A and the other say B, then A minus B is greater than equal to 2. This is satisfied, right? Because we have at least the greater than sign. Okay. So now C is also true. Now, since C is true, C says that there exists at least one root of one equation between 1 and 2 and one root of second equation between -2 and -1 such that the difference between them is at least 2. But the force says that any root bit of these two equations between have at most distance 2, so it cannot be true since C is true. So D is correct because it is the false option, right? So D is false. Okay. All right. I hope it's clear. It was clear. Question number 5. Let A belonging to R. Let fx and gx be two different functions on A to infinity. Consider the following statements. Okay. S1 says if limit x tending to A plus fx exists and limit x tending to A plus gx does not exist, then it is question on algebra that limit fx minus gx does not exist. That if one of the limit exists and the other limit does not exist, then does the difference of the two functions, then if we take the limit, does that exist or not? This is statement 1. Statement 2 is, now it's kind of a reverse, that if the limit of the difference exists, then at least one of the limit extending to A plus fx or limit extending to A plus gx exists. That if the limit of the difference exists, is the reverse true that one of the limits of f and g either has to exist. Okay, so we have to, the question is then, which of the following holds? Both S1 and S2 are true. S1 is true and S2 is false. Basically, we have to see if S1 is true or not, S2 is true or not. And then we can decide the option. S1 is false and S2 is true. Both S1 and S2 are false. Now, the first question, think about it, that if the limit of the difference exists, no, sorry, if one of the limit exists and the other does not, then can the difference exist? No, right? Because S1 is true. Also note that here we are only talking about the right hand limit at A because the domain here considered is A to infinity. That's why. Because the left hand, the points on the left of A are not even in the domain, then how can we talk about the limit? Then how can we talk about the left hand limit at A? Alright. So this one is true. Why? Because if limit x tending to A plus fx exists and limit x tending to A plus gx does not exist, if suppose limit x tending to A plus fx minus gx exists, okay, then can you see that limit of x tending to A plus gx also has to exist? Then why? Because gx can be written as fx or fx, you can say fx minus fx minus fx minus gx. Now, since both the limit exists, it is limit extending to A plus fx. We can separate it by algebra of limits, right? So this exists, some say some alpha, this exists, say some beta, then limit of gx is alpha minus beta exists. But this is a contradiction because we know that limit of gx extending to a does not exist. So if the limit of one of the functions does not exist and one of the function exists, so the limit of the difference cannot exist. Okay, so S1 is true, but S2 is false. That if the limit of difference exists, it does not necessarily mean that either of the limit has to exist. So one of the examples is, take a to be 0 and consider the function fx equals 1 plus 1 by x, and you can guess the function to be 1 by x, right? So both functions are defined on 0 to infinity, but limit x tending to 0 plus fx is infinity and basically does not exist. We say that the limit exists if it is finite. So uh, if it is infinite, we say that the limit does not exist. We just know that it is going to infinity. It is not any real number, right? So there are other scenarios where the limit does not go to infinity and the limit does not exist, like we have done in the previous classes. So we say that limit exists only when it is a finite real number. All right. So is an limit of x tending to g x is also infinity. So, but if we say if but fx minus gx is 1 and limit x tending to 0 plus fx minus gx is again 1, it is constant. So limit of the difference exists. So we say S2 is false. Because limit of the different exists, but these two does not exist. Alright. So our statement B is false. So the correct option is S1 is true, B, and S2 is false. Okay. Alright. Next is again a similar question. Question number 6. Again, let A belong to R. Let Fx and Gx be two functions, right? Hx equals maximum. We're defining another function which takes at each value the maximum of the both the functions. Again, consider the following two statements. About the function fx, gx, and hx. S1 is if fx and gx are continuous at x equals to a implies hx is continuous at x equals to a. Second is if hx is continuous at x equals to a, then at least one of fx and gx is continuous at x equals to a. Then which of the, again like earlier, which of the following holds? A is both S1 and S2 are true. S1 is true and S2 is false. S1 is false, S2 is true. D, both S1 and S2 are false. So your exercises, exercise firstly, consider Hx equals to minimum of fx and gx and do the same question. Okay, now this. So here the trick is that hx is the maximum of fx and gx. How can you express f the maximum function, minimum function in terms of f and g? Is this, that hx can be written as fx plus gx plus fx minus gx upon 2. Because why? Because if f is greater than g, so this will open in positive, right? Gg will get cancelled and we'll get fx. Hx has to be fx then, right? And again the other way around. So whatever is greater, we will get that value from this expression because of this mod, right? Similarly, you'll have to see how can you write the minimum function in terms of this. So I'll wait for 2-3 minutes. Just try to do this question. See that do S1 and S2 are true or not. Now it should not be difficult for you. Oh, I was muted for some time. I'm sorry. I will just quickly go through this again. So this function hx is uh continuous. If the function hx can be written like this, then by algebra of continuous functions, since fx and gx if are continuous at some point, then a mod of fx minus gx will again be continuous, then this whole function will be continuous, so s1 is true. But if the function hx is continuous, that it does not mean that the individual functions have to be continuous. Consider these two functions fx and gx, where fx is -1 for negative x and positive x is 1. For gx, it is 1 for negative x and -1 for positive. Then the maximum is clearly for x less than 0. Between fx and gx, the maximum value is 1, so it will take 1. And for x greater than 0, the maximum value between 1 and -1 is again 1, so hx will take the value 1. So hx is continuous for every real number since it is a constant function. But see that the left hand limit of f at 0 is -1 and the right hand limit is 1. So the limit is not existing at the point x equals to 0. So f is not continuous at x equals to 0. Similarly, gx is not continuous at x equals to 0, but h is continuous at x equals to 0. In fact, h is continuous at every x. So we have found a function such that the maximum of the two functions is continuous at a point, but at that point, the individual functions are not continuous. So RS2 is false. Alright. So the next is one continuity by a graph. So, so your question is, consider this function. Consider uh, the above function fx, whose domain is 0 to 4. Discuss the continuity at the point x equals to 0, x equals to 0, 1, 2, 3, 4. Okay, so see at x equals to 0. We have to check basically, what do we have to check at all the points? That limit x tending to a plus fx equals to limit x tending to a minus fx equals to f of a, which is to check that f is continuous at a. Okay, now I'll just quickly do this by graph. At x equals to 0, you see that f of 0 is 1. This point f of 0 is 1. Left hand limit at x equals to 0 is, left hand limit is 0, right? Sorry. So at x equals to 0, you just have to check the right hand limit because the left hand points are not even in the interval 0 to 4. So the right hand uh, limit at x equals to 0 is, where is the function going? At 1 only. So the left hand right hand limit is 1. So this implies that f is continuous at x equals to 0. Alright. Now at x equals to 1, it is the interior point of 0 to 4, so we'll have to check both the limits. So at f1 is, f of 1 is this point 1. I've explained earlier that this hollow points mean that they're not included in the graph, but this filled are included. So f of 0 is not 0 but 1. Left hand limit is at x equals to 1, the left hand limit is 0. At this point it is going, sorry, it is not filled, I should use a different color pen. It is 0 and left hand limit is 0 and right hand limit is 0, right? So the function is discontinuous. I'm sorry. The left hand limit here, the function is going to 1 is 0. The left hand limit, I'm really sorry for this. The left hand limit is 0, and the right hand limit, we have to go to 1, the function is going to 1. So limit is not existing at x equals to 1, right? So the function is not continuous at x equals to 1. In fact, the limit is not existing at x equals to 1. But what we can say is the function is right continuous at x equals to 1. Why? Because from the right, when we say, so there is another concept called right and left continuity. So right means if you go from the right, at that point, if the value of the limit and the function are the same, then we say that the function is right continuous at that point. At x equals to 1, because the right hand limit, when we go to from right to 1, the function is going to 1, and the functional value at 1 is also 1. So that's why it is right continuous at 1. Now coming to the point 2. So at the point 2, the functional value is 2, this point, right? F2 is 2, but yeah. And if we go from left, the function is going to 1. And if we go from right, the function is again going to 1. So the left and right hand limit are 1. But it is not equal to the value of the function at that point. So the function is discontinuous at 2. Okay. At 3, the function is very behaving very nicely. The function, when we go from left, is going to this point 2, for go from right again going to this point 2, and the function value at 3 is also 2, so the function is continuous at 2, right? Oh, sorry, 3. And now the endpoint 4, we do not have to consider the right uh hand side of 4. So the left hand limit of 4 is, when you go from left, the function is going to 1, but the functional value is whatever this point is, say 0.5. So the function value is not equal to the limit, so it implies that f is discontinuous at 4. So that's how you see the continuity and discontinuity via a graph. So you see that this was the example where we covered most of the scenarios uh, of a function being continuous or discontinuous. Like the best case scenario for is of a function being continuous is that it will have a limit, and the limit, right hand and left hand limit, are equal to the functional value. If the right hand and left hand limit are in the, in the domain. And this continues, either the limit does not exist, or if the limit exists, it does not equal to the functional value, right? Or we or sometimes the it is right or left continuous, meaning that the right hand limit is equal to the functional value, or the left hand limit is equal to the functional value, right? So these were some scenarios. This was the motive behind this question, to cover most of the scenarios, to educate you on how the function can be continuous or discontinuous. All right. Next is applying the algebra of limits on algebra of continuity. So the question is, at which points do the functions fail to be continuous? At which points, if any, are the discontinuities removable? Okay. So one concept is if there is a removable type of discontinuity, meaning that if the limit exists, but is not equal to the functional value, then we can you know replace the functional value with the limit. Then we say that the new function then obtained is continuous. This is how we say that that continuity or that discontinuity is removable if the limit exists but is not equal to the function value. All right. So question A part is yx equals 1 upon mod x plus 1 minus x square by 2. So this function is very well behaved. It is the difference of a polynomial and a modulus. Both of them are continuous. So it is continuous wherever it is defined. So the denominator a mod x plus 1, mod x plus 1 is never equals to 0 because mod x is will always be positive even if it is um because if mod x plus 1 is 0, then mod x equals to minus 1, which cannot happen because mod x is always greater than equal to 0. So this function is continuous everywhere, right? So there are no points of discontinuities. And next is yx equals x plus 2y cos x. Again, it is a polynomial upon a sine function. So it will be continuous everywhere where it is defined. So it is not continuous at the points 2n minus 1 upon pi by 2 and is an integer. So the odd multiples of pi by 2, there the cos x will be 0, so there it will not be continuous, it is not defined. So now is that a removable discontinuity? No, because even if you put the point, say pi by 2, the value of the function, sorry, the limit of the function is there is infinity. So the limit is itself not existing at that point, right? So not a removable discontinuity. Next is y equals x4 plus 1 upon 1 plus sine square x. So again, polynomial or a function with a root. So it will and denominator is trigonometric function. So it is continuous wherever it is defined. So, but we'll have to see where it defined. X4 is always positive. X4 plus 1 is always strictly greater than 0. So x4 plus 1 always defined. And sin x and is never equal to 0 for not equal to 0 for all x belong to R, because again sin x will be positive, greater than equal to 0, then it as a whole it will be strictly positive, so it can never be negative, right? So continuous everywhere. D, y equals 3x minus 1 1 by 4. So this you can write as 3x minus 1 1 by 2. So this is continuous wherever it is defined, that is on 3x minus 1 greater than 0, 3x greater than 1, x greater than 1 by 3. In fact, it can be 0 also. So continuous on the interval, right? And other points where it is discontinuous is not even defined there. So there is no that the function cannot even take that value there. So how can we talk about the removable discontinuity? Okay, all right. So one question on question number 9. Limits of composite function. Limit, evaluate the limit y tending to 1 secant y secant square y minus tan square y minus 1. So simply this is the limit y tending to 1 secant 1 plus tan square y is secant square y, so this will be y minus secant square y. So there is no denominator or anything. Just y secant square y minus 1. So if we put the limit directly, then it is secant of secant square 1 into 0. Though this is secant of 0, which is 1 by cos 0, which is 1. Just a warm-up exercise on continuity of, limit of composite functions. Limit x tending to pi by 6. This is your exercise, okay? Cosecant square x plus 5 root 3 tan x. Evaluate this, okay? Okay, so next question is, for what value of a is fx equals x square minus 1 x less than 3 2ax x greater than equal to 3 continuous at every x. Now see that at x less than 3 fx is polynomial continuous. For any point x less than 3, fx is like a polynomial type function. It is continuous for any x less than 3. For x greater than 3, strictly fx is 2x, again a polynomial, continuous for every x greater than 3. So the problem is at 3. So for 3, for you write at x equals to 3, for fx to be continuous at x equals to 3, we have to see that limit x tending to 3 plus fx equals to limit x tending to 3 minus fx equals to f3. Firstly, this limit has to exist. So 3 plus के लिए the function is 2a limit x tending to 3 plus 2a 3 equals limit x tending to 3 minus, for 3 minus function is x square minus 1. So these are polynomial, we can simply put the limit. This is x. So put the function 3, 2a into 3 equals 3 square minus 1. 3 square minus 1 is 8, 6a. So a is 8 by 6, 2, 4, 1, 4 by 3. So for this value of a, the function will be continuous at every x. So this was one part. I'm giving another part as an exercise for you to practice. For what value of b is the function gx equals x less than minus 2, bx square x greater than minus 2 continuous at every x. Okay, just try and do this. Okay, so question number 11. Discuss the continuity of the function x is 1 when x belongs to rational, 0 if x belongs to Q complement. So here we'll use the completeness property of real number. This is a very good question. So solution, we'll see the continuous. We have to see whatever points it is continuous. So we'll divide the whole function, whole domain R into rational and irrational. So firstly we'll consider the point. Suppose Suppose consider a point x naught belonging to R, it is rational. So we'll use the definition of continuity. Implies f x naught is 1, then choose epsilon equals 1 by 2. Now, for any delta greater than, so the continuity definition at x equals to a is for any epsilon greater than 0, there exists delta greater than 0 such that fx minus fa is less than epsilon for or x minus a less than delta. So if we say that the function is not continuous at x equals to a, negation is that there will exist epsilon greater than 0 such that for any delta if we take fx minus fa will be greater than equal to epsilon for all x minus a less than delta. This is how we say that the function is not continuous at x equals to a. So I'm choosing this delta to be 1 by epsilon to be 1 by 2. Then I will show that for any delta greater than 0, if I take, and I'm trying to show that at x naught f is not continuous. So for any delta if I take, and then in the interval x naught minus delta to x naught plus delta, that is whenever x minus x naught is less than delta, fx minus fx naught will always be greater than 1 by 2. All right. For any delta greater than 0, there exists an irrational number, not an, in fact there exists infinitely many irrational number in the interval x naught minus delta to x naught plus delta, say x. Okay, then it will implies fx by definition is 0. Then what we have is, then for uh then we have fx or here you can say that not continuous at x equals to a if there exists epsilon greater than 0 and such that for any delta greater than 0 fx minus fa is greater than equal to delta for, so since there was for all here, there will be for some x such that, yes, so it's not continuous at x is equals to a if there exists epsilon greater than 0, so that for any delta greater than 0 fx minus fa will be greater than epsilon, where x is some x, not for every x, only some x in the interval a minus delta to a plus delta. Then here we have fx minus fx naught equals 1 minus 0 equals to 1 greater than 1 by 2, implies by definition of continuity f is not continuous at x naught. Now x naught was any arbitrary point I took to be a rational number, so f is implies f is not continuous for any x belong to rational number. Similarly, if you choose an irrational number, you can again choose a rational number here between this point, infinitely many rational such exist. Then we say that again with the same argument, f is not continuous at any irrational number. So f is not continuous for any x belong to x implies f is not continuous. So this is anywhere. So this was an example of a function in which the function is not continuous at any point of the real number. Okay. Okay, so this was a good question. You should think more about it. Question number 12. Give an example. Firstly, if you remember, Sir has done this theorem. If f is continuous at x equals to c and g is continuous at f of c, then g of f composition is continuous at c. Now the question is, give an example. Give an example of functions f and g both continuous at x equals to 0, but for which f of g is discontinuous at x equals to 0. Does this contradict the above theorem? So the question is, if f and g are continuous at x equals to 0, we have to show that it is not necessary that f of g will be continuous at x equals to 0. But will it contradict the above theorem? It will not really, because the above theorem says that f is continuous at c and g is continuous at f of c. Then g of f is continuous at c. So we'll have to find a function f such that f and g such that f is continuous at 0, and but g is not continuous at f of 0. Okay. So one such function is to consider fx equals 1 by x minus 1 and gx equals x plus 1. Since both the functions are defined like a polynomial function, this is defined for x equals to 0, and continuous, this is not defined only when x equals to 1, fx. So both functions are continuous at x equals to 0. Now if we consider the function f of gx, what will it be? F of x plus 1. So this will be 1, f of x is 1 upon x plus 1 minus 1. And this is 1 by x. Implies f is not continuous at x equal to 0. It is not defined there, but not contradicts. So g is not contradicts the theorem because g of 0 is 1 and f at g of 0 equals to f of 1 is not defined. So f is not continuous at g of 0, so it does not contradict the above theorem. So these questions are good for your thinking, right? They give you a much better understanding of the concept. I've lost track of what question. So this is question number 13. Question number 13 is, if the functions fx and gx are continuous for 0 less than equal to x less than 1, could fx by gx possibly be discontinuous at a point 0 to 1? So the question is, if two functions are continuous on an interval 0 to 1, is it possible that fx and gx are discontinuous? It is of course possible, because you have seen, if we define function fx to be x, gx to be x minus 1 by 2, both are continuous in 0 to 1, but fx by gx is not continuous at 1 by 2 because it is undefined there, so it is discontinuous at x equals to 1 by 2. Alright? Question number 14. If the product function hx equals to fx into gx. So we have done certain questions on algebra of limits like the maximum, the difference, now the product. That if the function is you could have predicted the question by now that if it is continuous at x equals to 0, must fx and gx be continuous at x equals to 0? Of course, the answer is no. We have done many questions like this. So one of the example is example fx take to be identically 0 and gx to be the ceiling function. So f dot g is 0, continuous at x equal to 0, f is continuous, but g is not continuous at x equals to 0. The right hand and left hand limit are different. You can easily see we have done this type of question in previous classes. Alright. So in fact, can you construct a function in which both are discontinuous at x equals to 0, but the product is continuous at x equals to 0? Try to think about it. Okay. All right. So one question exercise. I'll just is it true that a continuous function that is never 0 on an interval never changes sign? Use the intermediate value theorem and think about this question on that interval. Give reasons. Okay. So that's it from my side today. I hope I was able to give you a better understanding about the continuity of the functions, the algebra of continuity, intermediate value theorem, and all of these topics. So we'll meet next week. Okay. I'll wait for some time. If anybody has doubts, let me know. Thank you.